Today we are going to talk about that beautiful thing known as projectile motion. And when we're talking about projectile motion, we're talking about anything that's thrown, shot, flung, heaved, or otherwise launched through the air and has a parabolic path. And the key to projectile motion, for something to truly be in projectile motion, once it's released, there's no other force acting on it except for the force of gravity. And so what that then gives us is two separate components, one which is changing continuously throughout the launch or throughout the path, the other one is staying continuous. And those two components are resolved from the initial velocity and act independently of each other, just like any other component. And when we really get down to it, we're not doing anything new. We're not looking at anything new here. We're still talking about forces. We're still talking about velocities, accelerations, and vectors. The only difference is we have two components to the motion. And as we've talked about before, we know vectors can act independently, and we can resolve any vector into its x and y components using that magical, mystical, amazing math we call trig. And so, if we have some initial velocity, which we'll call v, and we want to look at it, we can say that the bottom part's going to be our x, this side here is going to be our y. So there's some horizontal component to our velocity. There's some y component to our velocity. And we can find out what those specifically are. We'll call this v. We're going to call this magic doohickey here vx because it's in the x direction. We're going to call this one vy. And so what we observe, the observable motion of the projectile, is this v. But within that observable motion, we have two things going on. We have the object moving in the x direction, so from left to right or right to left, depending on which way it's going, horizontally regardless. And we also have the vertical motion, which is the y component. And the one thing to keep in mind throughout this is that the x component is uniform. There's no force acting on it in the x direction. So if the net force equals 0, then the acceleration equals 0. Right? The y component, however, is being acted upon by gravity, and so it is continuously or uniformly accelerating by a rate of 9.81 meters per second squared. Now, how do we calculate or how do we find these two magical mystical components of the initial velocity? I'll tell you. There we go. So, we have v, we have vx, we have vy. We have our angle, which we're going to call theta. That's a nice Greek letter, theta. Learn it, live it, love it. So, let's start with vy. Our y component is the opposite side from our angle, so we're going to use sine theta v. Our x component is the adjacent side, so we're going to use cosine theta v, where v in both of these is our initial velocity. Keeping in mind, of course, our x component is uniform and our y component is accelerating. At what rate? That's right, 9.81 meters per second squared. Delightful. But what happens after that, you might ask? I'll tell you. Our projectile is going to follow its parabolic path. We're going to imagine that this is a uniform, nice, beautiful parabola. Let's try that. Parabola. There we go. We got it. That has two sides, which if folded in half would be identical. Here on this side, we have an x component that's going to the right. We have a y component that's up to give us that net direction. As we're traveling up, what's happening to the y component? That's right, it's decreasing because the acceleration is from gravity and it's acting down until at this point here, the top, which we'll call, for easy reference, the peak, the v in the y direction is 0 meters per second. However, remember that the x component is, you guessed it, uniform. So the x component here is the same as the x component here is the same as the x component here. But on our right hand side, our y component is actually in this direction. Now the great thing about this, because it's a parabola, the Vy here and the Vy here, despite being in opposite directions, have the exact same magnitudes at the instant of launch and the instant of impact. Just different directions. So same magnitude, different direction. Our x components are, of course, the exact same. This, of course, assumes that the landing point and the launch point are at the same height. If we're assuming that, we can take that one step further and say that the time to the peak, the top, we'll call that, and the to down are identical. They're the same. Okay, it takes as long for the projectile to get to the peak as it does for it to get back down. And we saw that when we talked about acceleration in one direction. You throw something straight up in the air. You throw a ball straight up in the air. However long it takes to get up to that peak is going to be the exact same time it takes to get back down into your hand. Now we just have added that x component to the velocity. So if the time up and the time down are the same, what if we tried to find that time to the peak? Well, what do we know? We know the y component of the velocity, right? The initial, this is our initial velocity, Vy initial. And at the peak, we know that the Vy is 0. And we also know the acceleration is negative 9.81 meters per second squared. And so with these three things, we can calculate that time, because we know our equation for accelerated motion, Vf, equals Vi plus At. With a little rearrangement, this ends up time, and remember this is just time up, is equal to Vf minus Vi over A, and here the A is the acceleration. Notice here though that your final velocity, because we're talking about the peak, is going to be 0. And so your top number is going to be negative, your bottom number is going to be negative, canceling out, giving you a positive time, which is good. If you end up with a negative time, you've done something wrong. So then, if we know that our top and our down are equal, and we know what this is, we can simply multiply it by 2 to give you the total time. And then, with our total time, know, again, that our Vx is, that's right, uniform. And our only equation that we have to deal with uniform motion is V equals d over t. If we know the entire time that the object is in the air, t, and we know its initial velocity, Vx, which is also its final velocity, we can actually find how far it goes, what we call its range, simply by multiplying the exponent of the velocity times its total time. And there you go.